Section 1.4, Logical Equivalence. I was throwing this term around a little bit in the previous section. I don't know if you caught that, but we're going to talk more about it now. First of all, a tautology is going to be a proposition. Of course, it'll be a compound proposition, otherwise it doesn't really make any sense, is a proposition that is always true. So a compound proposition that is always true. That seems pretty special, so that's why we give it a special name. And then if we're talking about a compound proposition that is always false, that is what a contradiction would be. And of course, it would also be a compound proposition. Otherwise, it wouldn't really make any sense for it to always be false. So how might that happen? We have a little table down here. We only have a single propositional variable, so it's only going to have 2 rows, and it's just going to be P can be true or P can be false. So filling out the rest of the truth table, you might want to go ahead and pause and see if you can fill this truth table out. It shouldn't take very long if you've been following along. All right, hopefully that was enough stalling. Not P is false and then true for truth values of true, false for P. The disjunction P or not P, so true or false, is true, has a truth value of true. False or true is also true. On the other hand, true and false is false. False and true is false. So here's a very basic example of a tautology, which P or not P is an example of. And then P and not P is an example of a contradiction. What it means for 2 compound propositions to be logically equivalent is if they have the same truth values, regardless of the truth values of their individual propositions. So 2 compound propositions are said to be logically equivalent if they have the same truth values, regardless of the truth values of their individual propositions. Got carried away there. So let's investigate an implication. Remember the if-then statement and its contrapositive. So the implication would be if P then Q, or P implies Q. And remember the contrapositive was if not Q, then not P. So let's create a truth table that compares those two. So let's think about what all we're going to need in our truth table. So of course we have 2 propositional variables. So we know that this is going to be how many rows? 4. All right, make that longer if we have to. So it'd be nice to have some line paper, or at least a straight edge here. Okay, we're not going to need that little bit. I'm not going to try to erase it. Okay, so P, Q, we're going to need if P, then Q. We're going to need not Q and not P, so I might as well put them in that order since it'll be a little bit easier to read from left to right, in my opinion. And then finally the contrapositive, so I didn't make it quite long enough. If not Q, then not P. Okay, so once again, I encourage you to pause for a moment and try to fill this truth table out on your own, because that is something that you're going to need to be able to do. So let's see, I'll do the easy ones first. So of course the negations are just the opposite truth value. Not P is going to be false, false, true, true. Okay, and then remember again, an implication is only false if it's saying if true, then false. So P implies Q is only false for the second row. And not Q implies not P. Now I'm only looking at the previous 2 columns because those are the only ones that matter for this one. Is also, also only false in the second row. And for each of them, they're going to be true everywhere else. So as we can see, P implies Q and its contrapositive, not Q implies not P, have the same truth values regardless of the truth values of their individual propositions. So these are the truth values of the individual propositions. And I'll go ahead and put that in our notes, just this one. Truth values of individual propositions. And this is exactly how you would show your work. You basically circle those two columns and say something like logically equivalent. And then do a check mark. That's how you would show your work, to show that two compound statements were logically equivalent. This concludes section 1.4.